Hi everybody, I just wanted to make a quick video to recap what we did in class and do a few solved examples that will help you get a better handle on how to apply what we learned to actual problems. All right, first the recap. Take a look at this picture here, which it just shows the first 4 harmonic modes for a vibrating string. There's a few things that I want you to remember. First, all 4 of these harmonics can exist on the same string. So the string in all 4 cases has the same length, has the same linear density, has the same tension. Everything about the string is the same. What's different is the frequency of vibration and then therefore the wavelength of that particular standing wave. Remember that velocity equals frequency times wavelength. And so as long as the velocity doesn't change, and that only depends on material properties like tension and linear density, the frequency and wavelength are inversely related. So lower frequencies have longer wavelengths and higher frequencies have shorter wavelengths, and we see that in the harmonic modes. On the fundamental, you can see that you see just 1/2 of a wave at any given time is present on the string. When you shake twice as fast, the wavelength gets smaller, and now I can fit 2 halves or 1 whole wave on the string. Third harmonic, I can fit 3 half waves, and so on and so forth. So as the string vibrates in a higher frequency, the wavelength is going to get proportionately shorter. To figure out the wavelength, you simply relate the length of the string to how many half waves are present on the string at any given time, and you can work out the wavelength for a given vibration depending on what harmonic you're in. The other important thing I want to say about waves on a string, standing waves, and it's so important I'm going to write it down because it seems I might have raised an eyebrow for you that I talked about the velocity of a standing wave. How can something that's standing have a velocity? And remember what happens to create a standing wave. Especially in Mr. BH's little video, if you watched the little video that he posted as part of the assignment, standing waves, I'm going to write it, are made from traveling waves. I don't know how to spell traveling waves that interfere. Remember what's happening to create a standing wave. You either pluck the string or somehow you shake the string, and that generates vibrations that zip back and forth along the string. They reflect at the boundaries, and these are hard boundaries where the string is clamped at both ends. You've trapped this wave in such a way that it's going to reflect, and those reflections interfere. And the frequencies that are just the right frequencies will interfere in such a way that they always enhance and destroy one another to create a standing wave. And so these standing wave vibrations are made of traveling waves that are interfering in such a way to give the illusion of a wave that's standing still. And that's very important. Okay, so let's do some practice. So here's happens to be a standing wave that I've somehow set up on a string by plucking it or shaking it, or I've done something to make this harmonic. What harmonic is it? Remember to count the harmonics. To get the harmonic, you just count the bumps. So 5 bumps, 5th harmonic. Now let's go further. The string is 20 centimeters long. What's the wavelength of this standing wave? Well, I know there's 5 bumps on the string, right? So I can do 20 centimeters divided by 5, which would give me 4 centimeters. But that's the size of 1 bump. Remember, that's 1 bump is only a half a wave. I'm going to write that. 1 bump is 1/2 of a wave. And that's always true. Remember, a wave is a full up and down oscillation. And so you need to multiply that by 2 to get the wavelength. So the wavelength of this particular standing wave is 2 bumps worth of wave, which is 8 centimeters. Okay, let's go a little further now. The string is 20 centimeters long, has a mass of 4 grams, and a tension of 20 newtons. What's the wave speed? And remember, if you're saying to yourself, wave speed, it's a standing wave. Remember, standing waves are made up of traveling waves that interfere. So there is a velocity, and it does, even though you can't really tell, there is a velocity as the waves move back and forth along the string. And for waves on a string, the velocity is the root of the tension divided by the linear density. So let's calculate the linear density so we can use that equation. It's 4 grams, which you have to convert into kilograms, divided by 20 centimeters, which you have to convert into meters, and that gives you 0.02 kilograms per meter. And then the velocity is the square root of 20 newtons divided by 0.02 kilograms per meter, and that's the square root of 1,000, which I'm going to calculate. It's 31.6 meters per second. That's almost 60 something miles an hour. So even though this little wave is vibrating in place, it's made up of waves that are traveling along the string at 31.6 meters per second. All right, so now I can figure out what is the harmonic frequency. What's that special magic frequency that makes the fifth harmonic on this particular string with its particular linear density and everything particular about it? And for that, I'm going to use my wave equation because I want to relate wave properties so I can get frequency. I know my velocity was 31.6 meters per second, and from that earlier problem, I figured out that my wavelength was 8 centimeters by counting the bumps. Oops, 8 centimeters. And so I get, if I solve that, 31.6 divided by 0.08 is 395 hertz. That's the frequency of this harmonic. And so if you heard that frequency being played as a sound wave, you'd hear it as like a G. I think that's around a G on the piano. But let's stop for a second and just talk about what really happens when you hear this wave. Because we're going to spend a lot of time at the end of this week talking about the complexity of like what actually happens when you pluck a guitar string and play a note. A lot of things happen, a lot of different sounds get made when you play instruments, and deconstructing that is pretty complex. So we're not going to talk about that right now. But there is a little bit of a chain reaction I want you to understand. This string is vibrating at 395 hertz, but it's a string, it's not a sound wave, right? But that string is going to vibrate something else. Maybe it's the body of a guitar, maybe it's just shaking the air itself, but that's going to shake some other medium at that same frequency. Just like if you dip your finger in a little puddle of water at a frequency of 5 hertz, you're going to generate little waves that come out, little ripples at a frequency of 5 hertz. And so the string is shaking the air. The air then generates its own sound wave that, it responds to that at 395 hertz, and that travels at the speed of sound to your ear. Then your ear interacts with that vibrating, those vibrating pressure waves with the sound wave, and your eardrum moves, and that generates signals to your brain, and you hear that at 395 hertz. And so what happens when a string vibrates is it vibrates something else that eventually creates a sound wave in air that travels to your ear. So sounds that you hear from instruments are really chain reactions.